right? Okay, so section 1.1 is about the definition of functions. After this class, you need to clearly know the meaning of a function and also the components in a function. All right, let's get started. So in order to know what is a function, we want to start from what is a relation. So the first definition, the definition of a relation. Let me give you the definition. Anything that can be written as a set of ordered pairs is a relation. Okay? Anything that can be written as a set of ordered pairs is a relation. Okay? The relation looks like this. The braces is the set notation. Okay? The members, the elements in the set notation are the members of the set. A relation is a set of ordered pairs. So the members in the set, they look like this. All right? We use a parenthesis to frame the two components in the ordered pair. The first component we use x, the second component we use y, and then we use a comma to separate the two components and use a parenthesis to frame them. This notation in algebra, we use that to represent an ordered pair. A ordered pair, ordered here, emphasizes the order of the two components matters. Okay, let's say 2, 3 is different from 3, 2. If you switch the order of the two components, you will have a different ordered pair. All right. So that's the definition for a relation. Anything that can be written as a set of ordered pairs is a relation. And what is the domain of a relation? The domain of the relation is the set containing all the first components of the ordered pairs. All the first components of the ordered pairs in a relation. And then the range is defined as the set containing all the second components of the ordered pairs in a relation. So I'm gonna just change this to range. And change it here to the second. Okay, please have the definition written on your note. Taking note is important. The book is a lot of information, very thick. You don't need to read a book. If you have the energy, figure out the content on the notes, I can guarantee you have the A. Okay, the best way to understand what is a relation is to use it. Number 2, here we need to identify if there is a relation in a given information. If yes, find the domain and range for each relation. That's the requirement of number 2. Number 2, the first one, we see a table, right? It is a 2-column table. The first column, we have some persons' names. We have Alice, we have Bobby, we have Cindy, and we have Danny. The second column, we have those people's eye color. Alice has brown eyes, Bobby has blue eyes, Cindy has green eyes, Danny has hazel eyes. So that's the information we have in the table. Here we need to identify, do you see, here we need to determine, is there a relation in the information shown in the table? Do you see a relation here? Do you see a relation? What is a relation? Relation is a set of ordered pairs. Do you see a set of ordered pairs? The definition of a relation says anything that can be written as a set of ordered pairs is a relation.
Yes.
Yes? Okay. Do you think I can write the information in the table like this? I'm going to write the name of the person as the first component and write the person's eye color as the second component and use the parentheses to frame this ordered pair, right? First component is the name of the person, second component is the eye color of the person. So this is an ordered pair. This ordered pair corresponds to Alice, the information, right? Name, her name, and her eye color. And similarly, I can use an ordered pair to record the information for Bobby. Bobby, comma, blue. And then we also have, we also have Cindy, comma, green. And we also have Danny, comma, hazel. Right? So this is a set of ordered pairs. By the definition, it is a relation, right? Because the information in the table can be written as a set of ordered pairs. Very good. What about the domain? We use capital D to represent the domain of the relation. By the definition, the domain is a set, and the set contains all the first components in the relation. Okay, in the relation, we have 4 pairs, and their first components are Alice, Bobby, Cindy, Danny. So those names together make the domain of the relation, right? What about range? Yeah, we need to know the 2 names, the 2 concepts, domain and range. Range contains all the second components in the relation. So it has brown, blue, green, and hazel. So all the eye colors of the people in the domain, right? Okay, so this is how do we process the problem in number 2. Just identify if there is a relation, and write the relation. If yes, write the relation as a set of ordered pairs. The domain would be a set containing all the first component. The range would be the set containing all the second component. So far, so good, guys?
Yes.
Do you feel better about what is a relation? Awesome, very good. So next one, we have a mapping, kind of like correspondences in the graph. As you can see, we have 2 circle, like ovals. In the first oval, we have elements 1, 2, 3. In the second one, we have -1, 0, 1. And we have some correspondences here. 1 goes to -1, right? From 1 to -1. 2 to 0. 3 to 0. 3 to 1. Okay. Do you see a relation from the graph? Okay, that's correct. There is also a relation here, okay? The relation, because the information, the correspondences in the map, in the graph, can be written as ordered pairs as well, okay? Because we can write an ordered pair whose first component is the initial number, and whose second component is the terminal number. So this correspondence go from 1 to -1, right? So 1, 91 would represent this arrowhead, right? From 1 to 91, from 1 to 91. So that's the first correspondence. And we also have 2 to 0, 2, 0. We also have 3 to 0, so 3, 0. We also have 3, 1, 3, 1. right? And this relation also has 4 components, 4 members, and they are ordered pairs with the first component, the initial number, and the second component, the terminal number for each correspondence, for each arrowhead. Domain. Do you remember how do we find the domain for the relation? Domain, remember, it's the X.
Values.
Yeah, the first component, right? Very good. It is 1, 2, 1, 2, 3, 3. Okay, 1, 2, 3, 3. We have 2 threes. By the way, if you have repeating elements or members in a set, you do not write the same element more than 1 time. Like here, we do not write 3 twice. We only write 3 once. Yes, 3 appears twice, right? But we only write 3 1 time. Repeating elements in a set will be only written once. So that's the domain. Seems like the domain actually is the first circle, right? First oval. Yeah, the domain actually is the first oval. And range, by the definition, is all the second components in the relation. So the second component is 91, 0, 0, 1. 91, 0, 0, 1. Same with earlier. If we have a repeating element, do not write it twice, only 1 time, okay? So 91, 0, 1. Turns out the range is the second oval, right? So that's the second example about the definition of relation and its domain and range. Next one, number 3. Here we have a set of races, right? A set. In a set, we have 1, 2, 3, 4. 4 ordered number pairs. Okay, so is this a relation? This has to be a relation, right? This one is the most obvious one because it is given, it is shown as a set of ordered pairs. Yes, of course, this is a relation. It is a relation. Let's find the domain and range for the relation. The domain, we look at the first component, the yellow, I color it as yellow, 1, 1, 3, 5. Remember, repeating element only write it once. So it's 1, 3, 5. We use comma to separate members in a set. Range would be a set containing all the second components. So I'm going to use blue, 2, -2, 4, 2. We have a repeating element, so only write it once. So we have 2, -2, 4, right? So that's the domain and range for this relation. Continue. Number 4, what we have here is a graph in red, okay? In a rectangular coordinate system. Technically, we should have, this is the x-axis, horizontal scale, and this is a y-axis, vertical scale. The graph is in red, okay? The graph is 1, 2, 3, 4, 5, 5 points. 5 points. Do you see a relation? Do you see a relation? In other words,
Yes.
Yeah, you're right. Is the graph a relation? Yeah, it is. You might remember from Foundation Algebra 2, you have learned the definition of a point in a rectangular coordinate system, right? A point in a rectangular coordinate system is defined as an ordered pair, number pair. So this point is 0, 0 is at the origin. And this one seems like 2, 2. This one is 4, 4. And this point is -2, 2. This one is -4, 4. So the graph, which consists of 5 points, can be written as a set of ordered number pairs. We have -4, 4. We have -2, 2. We have 0, 0. We have 2, 2. We have 4, 4. We have 1, 2, 3, 4, 5. 5 points. There are 5 ordered number pairs in a set. So this, yes, is a relation. Domain. You should know how to find the domain, right? Can you tell me what's the domain and what's the range?
Domain is X and range is Y.
Yeah. Specifically, in the domain, we should have those yellows, right? Yeah, let me write it down. We have 94, 92, 0, 2, 4. And the range, I'm going to color it as in blue. Second component. And we have repeating elements. I'm going to just write them one time. So we have 0, we have 2 twos, but only write 2 one time. And the 2 fours only write it one time. As you can see, in this case, the domain and the range have different size. Earlier, the domain and range happen to have the same size. Those are just coincident. Okay, this domain and range both have 4 components, 4 elements, and this domain and range happen to have 3 members, but not always. Those are actually coincidence. In general, the domain of a relation and the range of a relation do not have the same size. They don't really have to. They don't really need to have the same size. All right, so this is number 4, right? Number 5. Number 5 is also a graph in the rectangular coordinate system. It is a straight line. It is a straight line. And let me give you the equation that represents the straight line. It is y equals x plus 1. Hold on. X plus, this is, yeah, x plus 1. You should have learned straight lines in algebra 2, right? This equation is the slope-intercept form. Y equals x plus 1 is the equation corresponds to the straight line here. Do you see a relation here? Do you see a relation? By the way, a relation is anything that can be written as a set of ordered pairs. Do you see a relation here? Okay, the answer is correct. But what are those ordered pairs? How do you identify the ordered pairs? Earlier in number 4, the graph only has 5 points, so it's easy just to write them out, right? List them here. But how many points do you see on this straight line? How many points on the straight line?
Many. There's a lot.
A lot, yes. Many, infinitely many, uncountably many. And the arrowhead means continue, goes to infinity, right? Yes, there are infinitely many, uncountably many points. There are infinitely many, uncountably many points on the straight line. And those points are ordered number pairs, okay? Those points are ordered number pairs. And we are able to write the points on the straight line as ordered number pairs and put all the ordered number pairs together as a set. And that set is a relation. But since we have infinitely many, uncountably many, it's not possible to write them one by one like what we had in number 4, right? And this is how we do it. In this case, when we have infinitely many members in a set, we do this. We write x comma y slash. Behind the slash, we write y equals x plus 1. And by the way, you do not have to worry about this. If you don't understand, that's totally fine. Try to understand. If you do not know how to write it yourself, it's fine. But try to understand what I wrote here. So this is a set. The set, the members in the set are ordered number pairs. And those ordered number pairs are solutions of the equations behind the slash. If the ordered number pairs are solutions of the equation, then the points represented by the ordered pairs would be on the straight line represented by the equation. So this set represents all the points on the line. It is a relation, okay? I want you to see that. Okay, you don't have to write a set yourself, but you need to see it. We do have a relation. all the points on the straight line, they are ordered number pairs. And we put all those ordered number pairs together, make a set. That is a set of ordered number pairs, right? So it is a relation. You agree, guys? You agree? Yes or no?
Yes.
Okay, perfect. The domain and range might be challenging. It's not like previous examples, and we see those first components and second components. And how should we describe the domain and range for this straight line, which is a relation we already agree, we already understand. How do we find the domain? Yeah, the domain is x. I understand. Is x, right?
Is it infinite?
Yes, x. But you cannot just write domain as x. You cannot just write that x. The domain would be a set containing all the values x could assume. All the values x could assume. So what is the domain of the relation?
Is it infinite?
I'm sorry, what is that?
Is it infinite?
Infinite? Very close. Okay, you want to do negative infinity to past infinity. Okay, so you might mean this for all real. All real. If you think about this point, you agree this point has x value 0. Do you agree this point has x value 0? This point is actually 0, 1. It does have x value 0, so it means 0 is in the domain, right? And then all those points, their x values are positive, all the way to positive infinity. And those points below this point, those points all have negative x. So the domain is all real. X here could assume any real numbers. So the domain of this relation is all real. The way we show, where the way we write all real, the set of all real is net infinity to past infinity. So write net infinity, past infinity, use a comma to separate it, and use a parenthesis to frame it. What about the range, guys? The range would contain all the values that y, variable y, could assume.
Is it the opposite way or?
The same thing, actually. The range is also all real. The range is also all real because this point has a y value 0, right? This big point has a y value. Yeah, I can, let me clean it up. This, oh, where's my line? Let me draw it again. This is a straight line. You might remember what is x-intercept, right? This point has x value, has a y value 0. Y value 0. That means the 0 is in a range. We're talking about y, values of y. It's okay, this is the first time we talk about domain and range for a graph, for a continuous graph. We have other opportunities to learn this again. And all the points here, they have a y values bigger than 0. Okay, bigger than 0. All the points here, they have a y value less than 0. So y value, a variable y could assume any numbers, could assume 0, could assume any positive numbers all the way to positive infinity, could assume all the negative number all the way to negative infinity. So the range is also all real. I have a trick actually can help you to identify the domain and range for a graph. Okay, listen up. It is very important. My trick to determine the domain and range for a graph. Look at this graph. This is a straight line, okay? To find the domain of the straight line, you look at the graph horizontally. Consider the graph horizontally. Okay, horizontally. On the left, by the way, this is extending forever, okay? Also, this is extending to infinity. Horizontally speaking, does this graph have a boundary on the left side, like a stop somewhere on the left. And on the other side, on the right side, does this graph have a boundary from the right, like either stop here or somewhere? Yes or no?
No.
No, you're right. It doesn't have a boundary from the left. It doesn't have a boundary from the right. In that case, the domain is all real, from net infinity to past infinity. Again, this is the first time we see something like this. Do not worry about that. We will repeat same type of problem later. For the range, we look at the graph vertically, okay? And this is going up, and this is going down. So this is going up, right? And this is going down. Vertically, does this graph has a boundary from the below somewhere, stopped here or here, Does the graph have a boundary from the below? Does the graph has a boundary from the above? Do you see it?
No.
No, you're right. It's extending forever to the infinity, right? Same thing on the bottom, continue until net infinity. Since it doesn't have a boundary from the below, it doesn't have a boundary from above, the range is also out. Okay, as I said, it's the first time we see something like this, and we will have other similar problem to practice. Okay, so we agree this graph is a relation, and we found the domain range for the relation. One more. Number 6, you are looking at a graph in a rectangular coordinate system. And this graph is a part of the parabola, okay? Part of the parabola. Part of the parabola, y equals x squared. But x is bigger than -3. You don't have to worry about that, okay? I wrote this just write this as a get a function or equation that can represent the curve here. If you don't see it, just don't worry about that. But you see, this graph is a part of the parabola, right? Not the whole parabola. The whole parabola looks like this. It's extending to infinity. This is also extending to infinity. Our graph here, number 6, is a part of it. Okay, look at this graph in red. Is this graph in red a relation? Yeah, let's go back to relation. Relation is anything that can be written as a set of ordered pairs. A set of ordered pairs. Do you see a relation?
No.
You don't see a relation? So what's the graph? Isn't the graph just tons of points? Isn't the graph just a bunch of points? Continue.
Uh-huh.
Yeah, and those points are ordered number pairs. And we put all the ordered number pairs together, make a set. And that set is a set of ordered number pairs. By the definition of relation, it should be a relation, right?
Yeah.
Okay, so let me write down a conclusion here. Very important. Please write this down. Any graph in the rectangular coordinate system, any graph in the rectangular coordinate system is a relation. Okay, let me explain why if you don't see it yet. Any graph, like this graph, like this, any graph, I can draw many different type of graphs, right? Those graphs are just tons of bunch of points, you know what I'm saying? And those graphs are just a lot points, right? Yeah, those graphs are just the points. Those points are ordered number pairs. So the graph is just a combination, a collection of ordered number pairs. Okay, graphically, they are a collection of points. Algebraically, they are a collection of ordered number pairs. And we know relation is anything that can be written as a set of ordered number pairs. So that's the reason. Any graph in the rectangular coordinate system is a relation. Please let me know, is that clear, guys? Do you,
Yes,
clear.
that makes sense.
Okay, perfect. Very good. Yeah, include this conclusion in your notes. Box it. All right, so do not worry about how do I write the relation as a set of ordered pairs. I'm just write it. You don't have to understand it. So I'm gonna write this graph as a set of ordered pairs. And those ordered pairs are solutions of this equation, okay? Again, do not worry about that. You only need to agree or see this is a relation, okay? So now the graph is a relation, and we need to find the domain and range for the relation. Use the trick. Let's look at the domain. To find the domain of the graph, we look at the graph horizontally. To see if the graph has a boundary from the left. Does the graph has a boundary from the left? Does the graph has a boundary from the right? Let's do one at a time. Does the graph has a boundary from the right?
No.
You're right. Perfect. It doesn't, so because it goes to infinity, right? So the right end point of the interval is going to be infinity because this curve goes to infinity to the right? What about the left? Horizontally, look at the graph. Does this graph has a boundary from the left?
Yes.
Stop somewhere. Yes? Okay, what is it?
-3.
Perfect. You guys are great. Yeah. It stops at the -3, right? It doesn't keep going. It stops at -3, horizontally speaking. And since, do you see we have a circle, like a hole, a circle at -3? We're gonna use a parenthesis to frame -3. So this interval means all the real numbers strictly bigger than 93. Do not include the 93 because at 93 we have a circle. If we had a solid dot, and you're gonna use a bracket. Do not worry about that. We have time to talk about that more times later. Do you see the domain, guys? Use the trick. Find the boundary from the left, find the boundary from the right. This is an open interval. I think you learned interval from Foundation 2. Yeah, I'm pretty sure Foundation 2 covers intervals when solved inequalities. All right, so that's the domain. What about the range? Range, then you're gonna look at the graph vertically. Top and down, bottom up, top down. Okay, does this graph has a boundary from the below? From below?
Yes.
Yes, what is it?
0.
Yes, you're right. Very good. This is the boundary from below, right? It doesn't go down more. There's nothing here. So the graph vertically, the graph stop here at 0. So the 0 is the boundary from the below. Since 0 is included, so we use a bracket. Let me explain why 0 is included. Because this point is a solid point. That point is on the curve. That point has has a coordinates 0, 0. So the y value is 0. That point is a solid point. It is a point on the graph. So 0 is an element in the range. So we use a bracket. So if it's included, bracket. If it's excluded, use parentheses. If it's a solid dot, bracket. If it's a hole, like a circle, parentheses. Okay, if you don't see all of them, it's okay. As I said, we will have other chances to practice the same thing. Does this curve have a boundary from above? From above? And
No.
this, no, yeah, you're right. The curve will continue. I just cannot continue forever, right? That's why we have an arrowhead here. The arrowhead means continue forever. So infinity. All right. We always use a parenthesis to frame infinity in for an interval. So that's how we find the domain and range for a graph in a rectangular coordinate system. Very important, you need to see any graph in a rectangular coordinate system is a relation. Okay? Yeah, how do we find the domain and range? Use the trick. Use the trick. All right, we have very good practice, I think, about what is a relation and how do we find the domain and range for a relation, right? And the focus of this section is what is a function. So now finally, we're gonna give you the definition for a function, all right? Let me write down the definition for function. Use red color. A function is a relation in which for each a function is a relation in which each x value every single each domain element only has exactly one corresponding range element. Okay, so that's the definition for a function. Knowing a function is a relation in the first place, but not all the relation is a function. What type of relation is a function? In order to be a function, the relation has to satisfy one condition, and this is the condition the relation need to satisfy. For each domain element only has exactly one corresponding range element. Okay, by sentence, it might not very easy to understand, but once I show you the example, you will understand right away. Okay, firstly, write this down. I can help you to understand the connection between function and relation. So let's say this is female. This is a human being. As you can see, all the females is a subset of all the human beings, right? Females have to be human beings. Females are humans first in the first place, but not all the human beings are females. In order for the human being to be a female, certain conditions must be satisfied, right? Physically, mentally, psychologically, yeah, there are requirements need to be satisfied in order for that human being to be a female. And the relation is the very similar relation and function. So let's say this is the set of all the functions, and this is the set of our relations. Okay, functions are relations, but not all the relations are functions. In order for a relation to be a function, that yellow highlighted requirement condition has to be satisfied. And that condition is for every single domain element, there's only one corresponding range element. Okay, you need to know the highlighted condition, and we're going to work on that. We're going to look at those relations we identified in number 2 and determine if those relations are functions as well. So let's start from the eye color example. So we agree earlier, this is a relation, right? And we wrote the relation as a set of ordered pairs. Now we need to understand, we need to determine, is this relation a function? does that condition is satisfied? What is condition? Look at your note. I just wrote it down. For each domain element, for each person, okay, there's only one corresponding range element. In other words, there's no same person has two different eye colors. Do you see every person only has one eye color? Nobody has two different eye colors, right? Yes? Or no?
Yes.
Okay. So if for each domain element is X, okay. So this is X, this is Y. If for each X, there's only one corresponding Y, means no people has two different eye colors, then that is a relation. Yes, sorry, that is a function. This is a function, okay? This is a function. This is a function. Because there's no X has two different Y's. There's no X has two different Y's. You know, a book I saw describe this. So X is the husband. Y is the wife. Wife, right? So Y is the wife. So if Y is the wife, X is the husband. The wife depends on husband. You know, in the older times, not right now. Right now, the women are very independent, right? In the older times, financially, wives depends on husbands. Once they get married, they don't work. They completely depends on the husband. So here, if the relation is a function, that means the family does not have a cheating husband. In which case the relation is not a function, in which case the family does not function, when the husband has two different wives. When you see a cheating husband, when the husband has two different wives or three different wives, more than one wife, and that family will not function. Okay, so the relation is not a function. In this case, every X only has a one corresponding Y. Each person only has a one eye color. So this is a function, okay? No cheating husband. What about this one? Look at the four ordered pairs. Do you identify a cheating husband? Yeah, again,
Yes.
X.
Yes.
Yeah, you see, yeah, who is the cheating husband? Who is the cheating husband?
3.
Yeah, exactly. We see two ordered pairs with the same X, different Y. With the same X, different Y. So it means the husband 3 has two different wives. That's not okay. That's not okay. So this is not a function. I hope this helps you. It sounds like a weird, a little bit funny, but it's actually could really help you to remember how do you know if a relation is a function. If you identify a cheating husband, not a function. If there's no cheating husband, it is a function. Okay. What about number 3? Do you see a cheating husband? Number 3 right here.
Yeah.
Yes.
Yeah, what is the cheating husband?
1.
1.
Yeah, again, X is the husband, Y is wife. You would ask why? How come Y is wife? Because Y wife, right? Y is wife, so X has to be husband. If you see a cheating husband here, the husband 1 has two different wives. Positive 2 and negative 2. So no, not a function. Okay, not a function. All right. So this one, do you see a cheating husband? You might see a cheating wife, but doesn't matter.
Yeah, there's no history.
And the funny thing is, if you see two pairs with the same Y, different X, like you see a cheating wife, but there's no cheating husband, the family still function, the relation still function. It's a weird society, right? Yeah, as long as there's no cheating husband, it is a function. Okay, this is a function. This is a function, okay? And also, I'm going to introduce one more thing. It only take 1 minute. Give me one more minute, okay? It is called a vertical line test. The initial is a VLT, very famous in algebra. VLT here represents vertical line test. What do we use vertical line test for? We use a vertical line test to determine if a graph, a function or not. We already agree any graph in a rectangular coordinate system is a relation, right? So we don't have to worry about that. Any graph is a relation. But how do we know if they are function? We use a vertical line test. How do we do the vertical line test? If we randomly draw a vertical line and there's no vertical line passing the graph more than one time, then the graph passes the vertical line test. If the graph passes the vertical line test, the graph is a function. Otherwise, it's not function. For example, if you have a graph look like this, like that, like a oval, this graph is a relation, right? However, it's not a function because look at it here. If I draw a vertical line, obviously the line cross the graph more than once, right? And those 2 points, let's say the coordinates is 1, 1. This is 1, -1. These 2 points have the same x, different y. The x value is a cheating husband, has 2 different wives. Okay, so we are going to talk about the vertical line test in detail on Thursday, and I'll give you more problems to practice on. I'm sorry that we did not finish section 1.1 because we had to use like more than half an hour to go over the orientation part, and I had to restart my computer. We will finish next time on Thursday. All right, guys? Thank you for coming today, and I'll see you on Thursday. Feel free to email me if you have any questions.
Yeah, I have a quick question.
Yes, please.
It's concerning the orientation on the lumen.
Oh, okay. So in Blackboard, right below Zoom meeting, do you see a link says how to enroll in Lumen? Click that. Click that. You will have the information for your enrollment. Yeah, you can take a screenshot, take a picture of it, or write it down. Right?
Under the syllabus, say that again.
I'm sorry.
Can you say that again?
Oh, let me show you.
Okay.
Let me log in again. No problem. And by the way, if